The last concept we want to cover from Chapter 17, talking about tree data structures, is the idea of a red-black tree. Now, if you remember, when we were talking about our list structures, we know that lists are provided for us in Java. We don't have to implement them ourselves. But what we did is we went through looking at different ways in which we could implement them, an array list or a linked list, in order to understand what kind of costs we incur when we choose to use an array list versus using a linked list. In the same way, what we're doing here in talking about the red-black tree is we're talking about the way in which a tree set is implemented in Java. A tree set is implemented with a red-black tree. So when you use a tree set, what you're using is a red-black tree, but you're using it as a user. You don't have to implement it. But we want to talk about the implementation of it so that you understand the costs that you're incurring when you use a tree set. And in fact, you'll see that it's considerably less than using a list of some kind. So now if we review where we've come from in our tree data structures, we started and we thought about how a linked list is kind of like a tree that only has one child, where each node only has one child. We can kind of imagine it like that. Now, a list in that way doesn't really get the benefits of any of the benefits of a tree, but it can kind of be thought of as a tree where each node has one child. Another way in which we could form a tree was thinking about a binary tree. A binary tree is like a list, but it has two children. And so at each node, there's a chance of branching out in two different ways. And typically when we implemented that, we called the two children the left child and the right child. We could go further and we could implement another kind of tree, a tree that has an arbitrary number of children, in which case we'd represent each of the children as a list of children instead of just two children in the instance variables. But backing up, what we want to do is we want to return to the idea of the binary tree. We showed how you could implement a binary tree, and then we gave some examples of different kinds of binary trees that have particular constraints on the way in which they hold data. One of those constrained trees was the search tree. And in the binary search tree, we said that the left side of the tree had to have elements whose data were all less than the node that you were currently at. And the right side all had data that was greater than the node that you were currently at. So that if you did an in-order recursive traversal of a binary search tree, you would end up getting all the contents of the tree in perfect order. If it's strings, it would be alphabetical order. If it was integers, it would be numeric order. If it was your class, it would be in the class that was dictated by the compare to method that you implemented. Search trees were one kind of binary search tree is one kind of constraint. Another way in which we saw that a tree could be built that had constraints was to constrain it as a heap, either a min heap or a max heap. A heap had the constraint that the root node had elements. In the case of a min heap, the root node had elements that were all great. The root node had the smallest element in the tree, and all the children had elements that were greater than the root node. In a max heap, the root node had the highest element in the tree, and all the elements below it had numbers that were lower. Two different ways of constraining a tree. So today what we're going to do is we're going to go back to the binary search tree, a tree that has two children at each node, a search tree so that the left side and the right side have the properties that the left side is less than the right side, and the node comes between both the left side and the right side. In addition to the properties that are associated, the constraints that are associated with the binary search tree, we're now going to introduce this other idea of coloring each one of the nodes. And the colors that we're going to use on these nodes are going to be red and black. The overall goal of why we're doing this is because we want to come up with a mechanism that enables us to make sure that our tree is very bushy. And by that I mean we want it to be as filled out as possible so that we get the benefits of the tree data structure, and the efficiency of the operations that we do on the tree are more like log n rather than the efficiency that we see on a linked list data structure, which tend to be more like n. The benefits of using a binary tree come to us when the tree has many branches that are equally distributed, that all the data is filled out in that tree. So red-black trees help us to guarantee that in a binary search tree, the data is filled out throughout the tree. Because remember, when you add things to a search tree, the order in which you add things to the search tree dictate the shape of the tree. Red-black trees correct that. So let's jump into it. A red-black tree is a kind of binary search tree, and the goal of it is to rebalance the tree using the rules that we're going to introduce with red and black coloring on the nodes, and we're going to rebalance the tree after every insertion or removal. It's guaranteed as a result that our tree's operations will have order n log n efficiency. And that was important because without this red-black coloring, we might end up in a situation where our tree had the structure of a linked list, and we would have order n efficiency, which is much less efficient. So what we're going to do is we're going to implement an instance variable within each node that identifies whether a node is colored red or black. Now we're just using the idea of color in order to differentiate the two different kinds of nodes. We're never actually going to visualize them or see them. We're not going to paint them so that we actually see the colors of red and black. What we're doing is we're trying to give each node a flavor so that we can restructure the tree. So each node is going to get a color, which is either going to be red or black, and that'll be indicated by an instance variable, maybe a Boolean that says is red, and that'll either be true or false. The rules of our tree are that the root is always going to be colored black. And another rule in our tree is that no red node can have a red node as a child. That's called the no double reds rule. No parent can have a red child. And the last rule that we're going to implement in our tree is that all paths from the root to a leaf have to pass through the same number of black nodes as every other path on the tree. So here's an example of a correctly constructed red-black tree that does not contain any violations of these rules. So for starters, let's examine the data that's held at each one of the nodes, the letters here. And what you can see is by examining the letters, you can see that it's a proper binary search tree. It's binary, so all of the nodes have two children, 0, 1, or 2. It's a search tree because at any given node, the left side has data which is less than the root node, which is less than the right side. So let's look at that. The root node has the value f, and if we look at the children, the left side has b, a, d, c, e. All those are less than f, so that's good. And the right side has g and h. All those are greater than f, so that's good. As we look down each one of the subnodes, if we look at the subtree that's rooted at b, we can see that the left child of b is a. That's less than b, so that's good. And the right side has d, c, e. All of those letters are greater than b, so that's good. So let's look at the subnode rooted in d. The left children of d are c. That's less than d, so that's good. And the right side are e, and that's greater than d. So that's a good binary tree. If we then swing over to the right side for the subtree rooted in h, we can see that the left side has g, that's less than h, so that's good, and the right side has no children. So for starters, we can see that this tree is a valid binary search tree. The next thing is to evaluate whether it's a valid red-black tree. Okay, well we know it's a binary tree, that's a precondition. We know it's got the search tree property, that's correct. If we look at the rules that we have so far, doesn't meet those rules. Is the root colored black? It is. Does every red node have a black parent and or a black child, meaning no double reds? And we can see that B, C, E, and G, none of them have a parent that is red. Now, if we look at every path from a root to a leaf, do all of them have the same exit cost? Meaning, do they all go through the same number of black nodes? Well, if we go FBA, that's 2. So 2s are sort of our standard. Is there any other way we can get from the root to a node without going through 2 black nodes? And as we look at this, we can see there isn't. We can go FBDC, that passes through 2 black nodes. Or FH null, that passes through 2 black nodes. FHG passes through 2 black nodes. So this tree meets all of the 3 constraints, additional constraints of a red-black tree. Black root, no double reds, equal exit cost rule. All right, great. So we can think of this this equal exit cost rule as perhaps a toll booth, meaning that every time we go through this tree, we're going to incur a toll. We're going to have to pay a cost every time we go through those black nodes. And it's we need to make sure that it's the same cost regardless of all routes through our tree. The exit cost is the same. Here are some examples of binary search trees. They're binary, 2 children each, 0, 1, or 2 children. They are search trees because all of the data within them conforms to the search tree constraint. But they're not red-black trees because they violate one of the properties. So in the top example, we can see that it violates the equal exit cost rule because there's one path through our tree, FBA, that costs 2 black nodes. But there's another path through our tree, FB null, cut out on the right side of B, that only goes through 1 black node. So this tree is not a valid red-black tree. All right, it violates the equal cost rule. In the bottom example, we can see that we have a tree that is a binary tree. It is a binary search tree, but it is not a red-black tree because it violates the double red rule. We have an example of 2 nodes where a parent and a child are both colored red. Now, these examples I show you because as we do operations on this tree, what we're going to do is we're going to describe how we insert and we remove elements from this tree in such a way that we maintain these red-black properties. And the reason why we want to maintain these red-black properties is because those red-black properties give us confidence that our tree is bushy. And here's how. The equal exit cost rule eliminates highly unbalanced trees. It ensures that you're never going to have a left or right path that's where one side is drastically longer or drastically shorter than the other. That means you're not going to be able to have null children very high up in the tree. And also the nodes near the leaves the nodes that aren't near the leaves are guaranteed to have 2 children. So it's going to make sure that we have filled out trees towards the top. Now the double reds rule gives us some flexibility to add nodes without having to constantly rebuild the tree, but it ensures that paths can't get too much longer than each other. Some paths can be longer than others, but they can't get too much longer than any one other. And it ensures that no path is going to be longer than twice the black height because we know we can't have 2 reds in a row. And so the highest a tree can be is twice the black height of the tree. So we haven't really introduced the idea of the black height, so let me talk about that. The black height of the tree is the exit cost. It is the cost of traveling from the root node along some path to a null node, and it's the number of black nodes that you pass on that path. We're going to call that the black height because it's the height of the tree if all you count are the black nodes. A tree that has a black height of BH must have at least 2 to the BH minus 1 nodes. So that would, for example, mean, imagine you had a tree that was completely full of black nodes. Well, then it would have 2 to the BH minus 1 nodes. So we know it's going to have more than that because we know that it's going to have greater than or equal to that because we know that it has some red nodes as well. And so if we solve for that by taking the log of both sides, we can see that the black height is going to be less than or equal to the log of the number of nodes in our tree plus 1. Now the flip side, if black height gives us a lower bound on the size of our tree, the red height is going to give us the no double reds rule is going to give us an upper bound on the height of our tree. Because what it says is that the total height of our tree, H, is going to be at most twice the black height because we can never have more than 1 red node for every black node. And so that means that the height of our tree is going to be less than or equal to 2 times the black height of our tree. And from our previous constraint, we saw that black height is going to be less than or equal to log of n plus 1. And so we know that 2 times the black height of a tree is going to be less than or equal to 2 times log base n plus 1. And what is nice about this is these properties give us a lower and an upper bound on the height of our tree. We know that traveling from the root of our tree to any point at the bottom of our tree is therefore going to be order log n. It's going to be at most 2 times the black height of our tree. And so we know that has a relationship to log n. And so we know that there's an upper bound which is related to log n of our tree. Now remember, this is different than our guarantee on a binary search tree without red black. because a binary search tree could have children just down the left branch or just down the right branch, which means that the cost of traveling from the root to a leaf in simply a binary search tree that didn't have the red-black properties could be n. Adding the red-black constraints ensures that the path is going to be at most log n. So these red-black properties, if met, make sure that our binary search tree with red-black conditions is going to be much more efficient than just a binary search tree. Okay, let's think about that for a little bit, and we'll come back and we'll talk about how we do operations on our tree. All right, thanks for your attention.